All right, this section is all about chords. Now, chord is a segment whose endpoints are on the circle. So the question is, why is segment RS congruent to segment UT? So we're talking about this chord and this one. Well, let's look at we've got a circle where Q is the center. And so all of the radii, each radius of the circle, are congruent. They're all the same size. The definition of a circle is all the collection of points that are equidistant from a single point called the center. And so we know all these radii are congruent. And then we have vertical angles here. And so by side, angle, side, these two triangles are congruent. If those two triangles are congruent, then the corresponding parts are congruent, and so SR would correspond to TU. And so that is the reason why we can, or one of the ways that we can show that those two segments are congruent. And so this final reason is by CPCTC, corresponding parts of congruent triangles are congruent. And what we previously stated was that triangle SQR is congruent to triangle TQU by side angle side. All right, you can pause the video and try this one. Similar to the last one, we can say all the radii are congruent. So now what we have is these two triangles are congruent by side, side, side. So we can say triangle BAC is congruent to triangle DAE by side, side, side. If those triangles are congruent, then the corresponding parts are congruent. So angle BAC is congruent to angle DAE by CPCTC. Corresponding parts of congruent triangles are congruent. All right, so now we can say if two chords in a circle or incongruent circles are congruent, then the central angles are congruent. Converse of that, if the central angles are congruent, then in a circle or incongruent circles, then the chords are congruent. We have another theorem, if two arcs in a circle are congruent, then the chords are congruent. If the chords are congruent, then the arcs are congruent. I'm not actually going to write out this proof, but I am going to kind of talk through it. We've got two chords in the same circle, and it says if two arcs in a circle or incongruent circles are congruent, then the chords are congruent. So we can assume, we can start with the given that these two arcs are congruent. Now let's draw in the central angles here. The measure of this chord and the measure of this arc and the measure of this arc are congruent, and those measures are the same as these central angles. So these central angles have to be congruent. All the radii in a circle are congruent. And so now once we get to this, we've got enough for side, angle, side, side, angle, side. And so those two triangles are congruent. If those triangles are congruent, then the corresponding parts are congruent, so we can get to those chords. And so chord AB must be congruent to chord CD by CPCTC. Another theorem here. If chords are equidistant from the center of a circle or the centers of congruent circles, then they are congruent. So since these are congruent, since the chords are equidistant from the center, then those chords have to be congruent. Since these distances are the same, then these have to be congruent. The converse of that is also true. If chords in a circle or in congruent circles are congruent, then they are equidistant from the centers. So if these two segments are congruent, then these two distances are the same. For the sake of time, I'm not going to write out the proof, but I'm going to kind of talk through what a proof of this would look like, all of the reasoning behind it. If chords are equidistant from the center. Okay, so start with FP being congruent to PE. And then if we draw in a radius, two radii, those radii are going to be congruent. And then if we look at these right triangles, you've got hypotenuse is congruent and you've got leg that's congruent, so those triangles are congruent by hypotenuse leg. Therefore, these pieces here, these segments must be congruent. And if those are congruent, then you can run through the same process to get to these being congruent by drawing in radii. And then if you add this plus this, that's going to equal this plus this. So that's the basic reasoning behind that. All right, so we're going to draw a regular hexagon inscribed in a circle. Now, a regular hexagon, all of the sides will be congruent, and there'll be 6 sides. You may remember from a previous lesson that the central angles for a hexagon always end up being 60. And so what ends up happening for a regular hexagon inscribed inside of a circle is that you can use the radius, and that will give you the side length for each of the sides in the hexagon. So start with drawing a point and then use the radius length. You would use this with a compass and draw an arc, use that point and the radius length to draw another arc, another arc, another arc, another arc. If you drew another one, it would go through point Q. And now what we'll do is we'll connect all of those, and we'll have our regular hexagon inscribed inside of the circle. We know all these are the same, all the sides are congruent because they were all that radius length. If you wanted to, you could split this up into 6 congruent triangles. Theorem 10.6 says that if a diameter is perpendicular to a chord, then it bisects the chord. So because this diameter is perpendicular to this chord, it splits it in half. Splits it into 2 congruent segments. The converse of that is true as well. If a diameter bisects a chord, then it is perpendicular to the chord. And I may have said radius. It works the same way whether this is just drawn as a radius or a diameter. Here an engineer is designing a service tunnel to accommodate 2 trucks simultaneously. If the truck can accommodate a width of 18 feet, what is the greatest truck height that the tunnel can accommodate? Subtract 0.5 feet to account for fluctuations in pavement. All right, so just for the sake of time, I'm going to do it this way. All right, so first of all, we can draw a sketch of that with just kind of the numbers and the expressions. We'll use x to represent the distance from the center to the to where the greatest height of the trucks could be. The radius here is 13.5 feet. So we've got a right angle here, and so we'll do the Pythagorean theorem. and we'll get for x about 10.06. And then we know that, let's see, we know that this is 13.5. And here, this is 13.5, so if we subtract 6 from that, we get 7.5 plus the 10.06 here. And then we need to subtract 0.5 feet for the pavement fluctuations based on when the pavement's hot or cold, it may fluctuate. And so add those two together, subtract the 0.5 for fluctuations, and so the greatest height that the tunnel can accommodate for trucks is 17.06 feet. The concept box of what we've learned in this section: if two chords in a circle or in congruent circles are congruent if and only if the central angles are congruent, and then also two chords are congruent if and only if the intercepted arcs are congruent. So if these two chords are congruent, then the intercepted arcs are congruent, and vice versa.